All right. So anti-clockwise is going to be 7 times 2, but it is minus, so it's going to be clockwise. Clockwise is so our convention we're using, we're saying anti-clockwise is positive. So it's 7 times 2, right? And then what else do we have? Those are just one forces. So the next force we have is, remember that there's nothing when you take moment at A that cancels. So the next one is just going to be what now? You have a minus 12 kilonewtons. Remember this minus 12 kilonewton? That one up there. So you have to put it in. Can't forget it. If you forget it, you get the problem wrong. And then you, for the moment now, it is a positive clockwise, anti-clockwise. So it's by times, what's the length of it again? 8, right? Equals to 0. So this is minus 14 minus 12 plus 8 by. Right, so that now gives us minus 6 plus 8 by. Right? You calculate that out because you guys know to do that. You're just gonna say by is equals to 26 divided by 8. And that gives you what's that value again? Work with me, guys. You can have a calculator out so we can move quickly ahead. So it's 26 divided by 8. So this one gives you 3.25 kilonewtons. Right? So you see what is important. This bending moment that you have here, you cannot ignore it. You use it in your bending moment part of the equation. So you get that one, and then you just substitute by in equation 1, and so you will get ay is going to be equals to what now? 7 minus by. So therefore you get 7 minus 3.25. So that gives you 3.75 kilonewtons, all right? So that's it. So those are important to you. Once you finish that, right? Once you finish that, you are going to just draw back your free body diagram, right? So you go down, draw your free body diagram again. So I can do a little bit better diagram. So you draw your free body diagram of the same frame, and everything must line up now. So AY was, what was AY? AY was 3.75. BY is equals to 3.25 newtons, right? And then you had one load here. That was 7 newtons, kilonewtons. Was kilonewtons and newtons? Let's make sure we're writing the right thing. There were kilonewtons. All right, so there are kilonewtons, right? So this is kilonewtons. And then you had right here, this was 4, 2, 2 each. Same thing across here. So this was 2, 2, and you had your moment. You draw back your free body diagram, right? Make sure you draw back your free body diagram. That's the first rule. And you put back your moment here. And you see a moment here. When the moment is going in a negative way, you're going to add. Those are the little tricks that just that curve on it you need to know. The next thing now we're going to do, we're going to draw our free body, our shear force. So the next part of the question will say, draw your shear force. This is our question. So you just put them in line with each other. All right, so this is your shear force part. And you start at 0, you end at 0. And bending moment part, where we do the bending moment, we normally have them in line. I don't know why. Oh, if I realize I didn't have enough space, I wouldn't start here. I can copy them, you know. And if I can copy it and carry it down. Because I don't want to draw it over again in the interest of time. Time is not my friend. All right, here. So let's put on a page and carry it down. This device is so cumbersome to work with, but I have to still try. All right. It's a little bit small. All right, so you draw them in line, right? Make sure you draw them in line. And then, so I just extend this part. All right, so, and then, so everything gonna be in line. Where you have your force, you can just put a little dotted line so you know where you have the second and the middle out of the beam, where you have the bending moment is somewhere at the center. So you don't have to measure anything. And similarly, you draw your bending moment below it. Come on, guys. And you draw the same thing right below it. So everything. So you can estimate it. You don't have to measure anything and draw. You just sketch it. So you'll have the same distance from top to bottom. Right? Right? So our distance, everything going down there. Right? Let me do a little cleanup because our time is the way. All right. Now, all right, what do we do next? So first of all, we're gonna draw our shear force. Let's analyze it. The first thing, I'll use a different color for clarity. So now let's get a different color here. We're gonna use something that you can see. So the first thing, we're gonna do it by ear. So we're gonna draw our shear force. Shear force is gonna go up. Where's my writer? Not even seeing it. Oh Lord, I can't see the green. Let me use red. So we're gonna go up, and we're going up, and you estimate where 3.75 is. So you go up there. So because this is your shear force, you know. Your reaction is your shear force right there. Right? And then now, so you draw it up there, so, and you're gonna come over. Remember, so this is 2, 4, 6, and then this is what? 8. 8 is measurement coming across. So where you go across now, the first point load, you need to come over there. So it's a rectangle map out, so it comes straight across. Now you have what coming down? A 7, don't? Isn't that a 7 coming down? So 7, you have a 7 coming down, a negative 7. So it's a negative 7 added to a positive 3.75. Right? And how much that gave us a while ago? Was it 3.25 or something like that? What was that value? 7 minus 3.75. What was that value? 3.25. So it's gonna come right down here. So now look at this now. So it's gonna come right down. Right? So you could say it right where it reach down here, so it's 3.25. But it is minus because I passed the 0. So remember down here, so it's minus, you know. Up here, so it's positive of the shear force. All right, so this is shear force. So this is where the 7 is. So if you notice between here and down here is 7. Right? This distance coming all the way down is 7. All right, the next one, it comes over and it's gonna go down now. So for the shear force, you're just going to follow whatever it have. So it's got to this point, and then you have another force down at point. It's B with the car down there, so it is A, this was A, and this is B. So it's gonna just go straight down to B. This is just the shear force. So you see it's easy for you to know. Because the shear force, this is 3 point. So remember, over B, you have 3.25 down at this point here. So wherever you want to call it, probably you want to call it C. So C is minus 3.25, but at B it is positive 3.25. So when you add those two, what you get? A 0. So it means it must close out back and go right up back to 0. Right? Now, the area underneath your shear force is equivalent to your bending moment. So this is what I want to show you with the simplest of one. All right, so we know that I'm still fighting with these icons, zoom icons in my way. So these, you have, so the area underneath your shear force is equivalent to your bending moment. You remember I told you that before? Anybody remember? You guys are with me? So this here, look, see them here? So that area, what area is that? And what area is this? So we're going to look at the areas individually. So we're going to label them. So we're going to call this, so this was A, call here so C, call here so D, call here so E. All right, and we're going to represent them down here. So this one is C, D, and E. All right, so for the first one, And remember, this one was A. For the first area AC is a rectangle, not true? What's a rectangle? That's the area, and it's positive. It's a positive bending moment this is going to give because this is 3.75. The height of the triangle is positive 3.75. The length of it is what? 2. So you have a force times a distance, right? So that is giving you the moment. So the bending moment is going to be equals to positive 3.75 kilonewtons times 2 meters. So therefore you get, what is that value now? 3.75 times 2. What do we get here? 7.5? Was that correct? Or did I have the right figure? Make sure I have the right figure, right place, Let me make sure. What was do I have the right figure? A was 3.75, right? And B was that. Make sure. All right, good. So that giving me 7.5. Is that correct? Are you guys with me? Are you just there? Are you not with me?
No, we're there, man, sir.
Yeah, 3.75. So what's the difference? We're working on the era. Let's work with me now. Just making sure. So the first one is 7.5. So the 7.5, we're gonna draw the BM now. So we got the first area 7.5. The BM we got simple support BM. What did I tell you say with the simple support BM? Is for the rectangle area, when you get a rectangle area, you get a slope. So we're gonna estimate it, you get a slope. So see here? So you get a slope. The area bend what we get. So the BM, this is a bending moment. So this part represents 7.5. Positive 7.5. See it over here, positive 7.5. So this gives you positive 7.5 kilonewtons meter, right? So that's what gives you there. What happens for the next section here? The circle section here now. Can I give it a different color? This section here. What happened to this section? That section there now is the same thing because area CD is going to be equals to but this is minus 3.25. And what's the distance? 2 again. So that now is gonna give us minus 3.25 times 2 give us what? Minus 6.5. Not true. So
Yes,
minus 6.5 added to positive 7.5. So look, you see right here, you're gonna add them. 7.5 minus 6.5. How much you get there? So you're gonna get what? 1. That's all. Now 1 you get? So if you get 1,
yes, sir.
you
Yeah.
need to drop down to 1 down here. Right? You remember that? So it drop to 1. So this is value down here. Right down at the bottom here. So where is it? Come on, writer. My writer's gone. Not seeing it. Oh, so we're at the top. Let me get like a dark writer so I can see it. So this is minus 1. Sorry, positive 1. So positive 1 here. What did it have at D? At D, no, it didn't have anything at D. I say it go. Was it, make sure my diagram right, It was at C we had it. Okay. All right. So it dropped that down to here. Hold on. Oh, is D the force was that? Where did I get it at E? The force wrong, man. Let me take out the force. The force, where we have that force is the bending the moment here. Lord, I can't. You see this force right here, sir? At the wrong place it is. This one. It was at here. If I'm looking good at the drawing, it was right here. It was right at B. So we have the moment at the wrong place. Who understand what I'm saying? This moment is at the wrong place. So this moment here was what? 12 kilonewtons meter, right? It is acting at B right here. So now you need to add it in. Once it is going in the clockwise direction, right? But it's gonna end up based on convention, it's going to give the beam a positive bending moment, right? So it's going to be twisting beam in such a way to give it a positive bending moment. So when you're adding it down here into your graph, you're going to be adding 1. And remember, look at the direction that it turns. You see the direction it going into the clockwise, which is supposed to be minus, but based on how it turns the beam, it is going to convert it to a positive. So it's going to be 1. And then what value is it? 12? So it's 12. Right. So this is our point. You could have said bending moment at D. Right? So it is 1 plus 12. So that gives you 13 kilonewtons meter. So right here, right here, are you going to be in a straight line? So this is A. We call that C, or we call it D. So it's gonna come straight up and give you wherever 13 that line. So it's gonna give you 13 right up here. All right? All right, and that is just pure by inspection. Remember, this was drawn in the incorrect position. So this diagram up here, this bending moment is actually at the wrong position. It should be at it should be right here. Looking good at the diagram, it should be right here. This is what I have it as, right? We can look at our original slide. I think that was where it's supposed to be, right? And that is 12. So that is what I am correcting, 12 kilonewtons. All right, yeah. All right, let's go back down to where we were. So, okay, now that we have 12 up to this point here, so, right here, it's just straight on now. We're gonna go back now and we're gonna calculate area again. The area that we leave with now is DE. So let's calculate area at DE. So area at DE. So the area at DE is another rectangle, not true? And it maps out. This is still minus 3.25 times 2. So it gives you another positive what? Negative 6.5 kilonewtons meter. So you're gonna add that, right? You see the 13? So you're gonna add the 13 to that. So 13, and then you add the 6.25. So you're gonna get 6.5. So it's going to be 6.5. So it's going to drop down to 6.5. And remember, it's a bending moment, so the area underneath a shear force for a simple bending moment is just a slope. That's all you need to remember. So right here, right, it's not drawn to scale, please remember. So this is representing of positive 6.5 Newton meter. So remember, I said the thing is in Newton, a Newton meter, right? So when you come here, all right, so that is coming at this point here. Now coming up, so it is going down, right? So you remember, say it's going down. That is going down, right? And then you have what about the other area right here? So what's the area being EB? The area underneath EB. So area, right? At EB is another one. Same thing, same rectangle. So which is what? 3.25 times 2. So it end up to give you our minus 6.5. Not true. All right. So if this is a positive 6.2, so we're right now we're right here. So therefore, and this is what do we call this? EB. So all you're gonna add is minus, so at this point is 6.5 positive, and then you add it to a minus 6.5. So therefore it tell you that it goes straight down to 0. See there? and you bend the moment finish. See that? That would have worth 20 marks in exam, for example. All right? Simple, that's simple as that. All right? All right. Now, how much time we have left? We have any time left? We're gonna do another one. All right. So that is simple shear force bending moment. That is what all everybody are run from. All right. Let's do another one. Let's come out of this. We're gonna drop this and go back into our slide. So okay, we're gonna do which one I want to do now. Let me tell you the one that I want to do. This one. Yeah. Want to see it floating there? We're gonna do this one. All right. Okay. So this one, you're gonna do the same thing, right? I'm gonna take it and I'm going around to the zoom along page. I'm gonna copy it. Let's copy it. All right. And I'm going a little bit fast. If you stop me if you don't understand something, please. All right. So let's add a page to this, and I'm gonna start on a fresh page. All right. This is what everybody tell me they're going to run from. All right. Oh, why is it doing this? I wanted it. Hold on. I want it here. And then I say, give me another page. Yeah, I want it down here. I don't want it in between here. So I'm then gonna paste it. Yeah, so this is it. All right. You guys remember how to calculate the reaction to this one? Talk to me. All right. So we're gonna go through it very quick. All right. So for this one, it says you must get the reaction at AB. And the same thing I would ask typically on an exam paper or anything. I'd say get AB. All right. So it's same thing. So you're going to do, let's go for it now. You're going to draw your free body diagram. All right. You draw a free body diagram. And remember, your UDL is going to be converted to a, can anybody tell me what do you do with the UDL? Talk to me now. Someone hear me? What do I do with the UDL?
Sure,
Hello?
you convert it in a force that is acting on a single point.
Yes, you convert it to a concentric load, a point load. So I'm going to convert this. When I convert it, how do I convert it? I know 200 Newton meter times the distance is what? 2. So I multiply by 2 and meter. So now I end up with 400 newtons. So this now becomes 400 newtons. This is 400 newtons. At this point, I have a moment here, right? So any moment calculation it involves. All right, so this is now AY, and this is now BY. All right, so we're moving up. All right. So all we're gonna do, so we can label this CDE again. All right. Okay, so let's find these forces quick. So firstly, and you notice, so here now you're gonna say that the sum of your forces in your y equals 0. So you know AY plus BY. Right? Then you have minus 400, another minus 400 coming down equals to 0. So this can be written as AY plus BY minus 800 equals to 0. Quick and easy like that. All right, the moment now, we know that this distance here is 2. This is 2, and this, all of them are 2. And this is 2. All right, so there are 8 coming down. So let's take moment at A to get rid of one of the unknown. So we take moment at A. All right, so the first one would be minus, and we're taking anti-clockwise again as positive. 400 times 2 minus 400 times how much is time? 4, right, at D. And then now, we know that we have a positive 200 going up at E. See there? Positive because it's going into the clockwise direction. So that's positive. So you had it there. And then the last one would have been 8, times BY equals 0. And this work out to give you, this is what? Minus 800 minus 16. And my correct there for, tell me if I'm wrong, plus 200, right? Plus 8by equals 0. What that works out to be? That works out to be, so that was what? 4 times 400. How much is that value there? That is minus 800 minus 1600 plus 2. I'm getting minus 22. Is that true? Am I correct so far? Body working with me? by equals to 0. So from this, I can say by is equals to 2200 divided by 8. All right? Am I correct so far? Anybody with me? Yes or no? Gentle folks, are you there with me?
Yes, sir.
Something is wrong, man. And what did I put? So this was 4 times 2. I'm just checking the value here. So it is so it's 4 times 2. What was the distance here? Let me check about the distance. Oh,
So
you
you
know
say
the
you have
distance, there are
400
one.
times,
You know the distance them wrong?
yeah, so you
Oh
have 400
Lord.
times 4.
There's what the distance them wrong, you know, one them. Oh Lord, because I can't see it. One and
Yeah, I
nobody
do
tell me.
400 times 4.
Ah, yeah, so there are 1. And this is 2. So this is 5, 4. So that means, let me correct it. You see, I can't see the thing while I work in it. I was just trying to remember what was the distance there. In fact, I wrote them wrong initially. So we have to be careful. Make sure you write them and draw them in right because you're going to get it wrong. So this is 1, 1, 1, 1. So the distance is 4. So the first one would be times 1. The next one is times 2. And this one is times 4. So that
Yes,
means
sir.
order down here so is erroneous. Let me just clear them out.
Yes, sir. I have it. That's very confusing, man.
What's that?
No man says you have to be careful.
Yeah, because you
Catch
see,
me too
because I'm
sometimes.
doing it and I can't see the entire page. Because
Yes,
it's
sir.
on
I
half
understand,
page
man.
I'm seeing. I'm using a smaller laptop now and I can't see the laptop. So it is minus 400 times 1 minus 800 plus the 200. You know, everybody know where the 200 come from. It is this one right here. This moment, it is going clockwise, anti-clockwise, so it's positive. You
Yes, sir.
remember that?
Yes, sir.
Plus 4by equals to 0. So this part works out to be how much? 1,000 minus 1,000, right? So that's
Sir,
1,200
me
minus
have make it.
1,000 plus 4by equals to 0. So therefore, by is equal to 1,000 divided by 4. So this is going to give me what? 250?
Yes, sir. Correct.
Newton, right. So therefore, I'm going to substitute that value. Substitute by in equation 1. All right. And so that gives me, God gives me that AY is going to be equals to 800 minus BY. And doing that, I'm going to get 800 minus 250. What's that value I should supposed to get there now? 550 newtons, right? Okay. Now that we have done that, so we have calculated the reactions. So all you're going to do is convert wherever you say the UDL, convert it to a point loading. Done. Simple. All right. Next thing now, we're going to redraw it down. I want a nice fresh page. Let's get a fresh page here. See if I can find an icon to get the fresh. We're going to draw it back again here. So I'm going to draw it back here. And please remind me, let me try and find my notes. So I guide myself because I can't see the screen up here. Yeah, all right. So we draw it back, put a load here, and put another one here, coming down. So this is AY, this is BY. So all this is so easy though. You don't have to worry about it. It's easy. If you do it
Yes,
by
sir. Simple,
era,
man.
if you do it by era, it's simple. It's just that you have to just watch what you do. We had a moment here, which is a 200. So this one was 400. We had converted UDL. This is now 400. So it's simple, you know. So it's A, B. You just have to concentrate. C, D, E. Remember, you don't have to use method of section. You can do it by inspection. Once you remember how to do, just the principles that you need to remember. The next thing you're going to do now, you're going to draw your shear force and bend the moment on it. Give myself enough space. And this is my shear force diagram. So it must come in line with this. So it's a sketch, you know. Remember, when I expect you to draw nothing with no measurement in exam. And then you do same thing with this one. Pardon me for my sketches. My sketches are not perfect. This line here is very lean. All right. Right. All right. Okay. Now, after you do that, so this is shear force. And down here is BM. So this one up top is force, one is BM. So one is in Newton and one is in Newton meter. All right. So we put in the value of AY. AY was what again? AY, remember the value. I'm not going to scroll up. AY was 50 newtons, and BY was what? 250 newtons. All right. So for the first thing, I can draw them. Looking at the figure, I can just draw them in. Let me get a different color. Red. So I'm going to draw them in. Maybe I need to clear this away when I'm drawing so you can see it. Just for clarity. So I'll clear that away. So you're coming up and you're going to come up 550 newtons. So 550 Newton, you come up there. So, all right. After you come up there, so you're gonna go over to the next one. So it's all right. The next thing is a UDL though. So what did I tell you about a UDL? When it's a UDL, what happens? Do you remember what happened when it's a UDL? So you're gonna draw it, you're gonna map these distance down. So the 400 will be somewhere there.
Oh, so you say they're gonna be on parabola, no?
This is a shear force part, you know.
My
For the
bad. Sorry.
bending, remember, up here is where you have your UDL. So for the shear force for your UDL, the shear force equivalent is a slope. So you're going to slope it over to right where the BM. The BM span from 1 to 2. You remember? So you're going to draw it coming right over to this point. Right over here. A slope. Right? That is not even looking like a slope. It bend up. It's a straight line, but it's a slope. See a sloping line are coming across. Once it's a UDL, the UDL section is a slope. And you know why we stop right here, so? Because right here, so, you have a 400 coming down here. So the difference between you have a positive 550, but you have a negative 400 at that point. So the difference is going to give you what? 150. So right here, so up here, so is 150 newtons right here, so. Right at that point right there. You see that point I'm put there, so? Right at D. So it don't come down yet. All right. Let me see if I'm correct there, so. Did I get it correct? Yeah. Right, so you come right there, so. That's it for the first part. Get 150. All right. Now, so it stopped here. It stopped here, so. Right? That is for the first 400. That's for the first 400. This 400 here. You see, for the second 400 now, it comes in, you know. So that's for the first 400. For the second 400, you're going to take, it's gonna come down straight, right at 2. So for the first one, it's going to, the one that we actually, this one is right here. All right, so it shows you that it comes down 150. All right, it shows you that the value comes down 150. Here, for the second one now, it's going to be 400 coming down. So if this is positive, this distance is 400. You have 150 plus 2, so you have 150, because this is positive 150, right? The positive 150, you have a negative 400. So that's gonna give me what? 250, no so? So right down here, so where it reaches is negative 250. Do you agree with that? So right, this force here, coming right here, so see there? It come down negative 250. This one carried down to this point. So it moved from, so from here, the 550 come down to this point. From this point, it tells you that this is kind of carried down right down to this point. So you just draw a straight line, a straight slope coming down to this. So right down to the end of it is a slope, right? Now, here now, so it's 150, right? But you want probably ask yourself, how comes it's 150? Because 400 from this first 400 minus this give you 150. So it will stop here. After this 400 now comes in being, and it comes straight down, carried down to this point, says minus 250. All right, cool. Now that you have done that, we are just going to draw. And remember, the moment don't come in this because it's a moment in the moment diagram. It's just shear, just force you're dealing with. So you have a positive 250 here. You're going to go straight out to B. Okay, it maps a rectangle. Once it's not a UDL again, it maps a rectangle area. So this is minus 250. But out at this point, don't you have another force out there? A positive what? 250 at this point. So if therefore at B, you have 250, then added to another positive 250, you're going to get 0. So then it goes right up to this point, and it closes at 0. So you start at 0, you close at 0. Now the area underneath this graph, what is the area being mapped out? This is a trapezium, right? All of that is a trapezium. This is a rectangle. Those are your bending moments. All right? So you see, that's done. And how did I get the slope? Because for your shear force, for a compound beam, a UDL beam, your shear force is a slope. And for this over here, so it's just a regular beam. Over here, so from D to B is a simple beam. So it's a simple beam, it just map a rectangle area. All right, I know we're almost finished. Can I finish this curve here? All right, this curve here is hello, are you hearing me? This curve now. All right,
Yes,
so
sir.
let's find the area. Let's find the area quickly. So we have A, what do we call here? So we have AD, call here so D, all right? And then this is B. So we're going to find the area under AD. So the area under AD is mapped to what? Now trapezium. If I can draw the trapezium looks something like, let me see if I can draw it. Top, straight back. If I turn it the other way and just draw it. So it maps a distance like that. Now what's the height of the trapezium? The height of the trapezium is what? 2. This force up here so is what? 150 positive, and down here so is 500 force. So 150 Newton, 500 force. What is the area under a trapezium? Area underneath a trapezium, which is AD here, is equals to half the height, perpendicular height, times the sum of the parallel side, A and B. So this is your A, this is your B, and this is your H. So therefore, we are getting the area of it. So from that, it simply says that half times the height is 2, and the sum, the area. What's the area again? So the A is what? 150? A is 150. Let's move these icons out. This laptop is so small. 150, not ideal to teach at all, plus 550. All right, and that gives me, so half times 2 is 1, and you sum these two together, you get 550, you get what? That's 700. Do you agree with that? So you get 700 Newton meter. So remember that the 2 is in meter, you know, and these forces are in Newton, so you get Newton meter. So that's the area. So what you do now, you come back over here and you say, okay, all right, let me move this out of the way for clarity, because I want to make sure that you see what I'm doing. I'm changing the color of the axis. So let's pick up a different color writer. Let me see if purple or blue I want to do. Let me see if blue will work for me. Come on, where's the writer? Boy, this thing is so small. Sometimes I can't find it. Let me use the mouse and get it. All right, I pick up a blue one. I'm going to look for see if I can find it down here. Yeah. So here now, you're going straight up. Sorry, I'm going to draw back the axis. So this is your axis. And the axis that is. So now we're going to draw it. See? Let's mark the point. Right? And the other point was here. The next point was somewhere in the middle here. And the last point was these. So remember, you don't have to draw anything. So this is A and this is D. So it comes up to 700. So 700 is a parabola. It pops up right up here. Do you see that? So this point up here says positive 700 Newton meter. All right. All right. Now, all right, what about the other area now? All right, so first of all, the next area we need to calculate. Let's do them in part. We could do it in one go, but to make it relevant, we are going to consider this little area here. Let me clear it out and give it a different color. This area here, we need to find this area here separate. Let's find this area here separate. Let's get another writer, and I'm gonna highlight it. So this little area here. What's this area here? So that area is, let's calculate that area. That area is down here like that. And what distance is that area mapping? It maps, I think this was C, and then this was E. So we call it DE, area DE. So area DE, right? Oh, all right. So what's the height? The height of it is a rectangle is minus 250. And what's the distance? No 1? So it is 1. Right. So therefore, 1 meter. So therefore, the area is the length times width or height times width. And this is in Newton, and then this is in 1 meter. So therefore, you're getting minus 250 Newton meter there. All right. So minus 250 added to positive 700. You're gonna get what value there now? So it's going to give you so remember, underneath your shear force, once it's a simple support beam, DB is a simple support beam, you should be getting a slope in your bending moment. So for the shear force section, it's a slope. No, it's a slope you're dealing with. So it's going to be a slope. So the difference between 700 and minus 250 gonna be giving me what value am I supposed to be getting? That's 700, right? Minus 250. So I'm getting 450. So drop it back down to 450. Oh, that don't look like 450. That look like something different. Let's clear that up again. Let's get the right again, a little bit more accurate. Something more like that. I think it should be a higher up. Higher up is looking something more like that. Still not looking perfect. We're almost done. So see there, this is how easy it is. And the only little things you need to remember is the ear underneath the bending moment for a simple support beam is a slope for the beam. Right? So and this is, what should I say? 450. All right. At E now, you have another moment there. What is this moment doing? Once it is turning in the, and this is it now. So it is going to, as far as my concern, turn the beam into a different direction. So it is going to make the beam hug. Am I using the correct term? Let me see. It's going to make the beam turn in such a way that it becomes negative, give it a negative effect. In my estimation, it's gonna give the beam a negative effect, right? So you have it's a positive bending moment, right? It should be really, you would want to say it's sagging, but it's gonna give it an hugging effect because it is turning up. And this is the only trick to it that you need to remember. Where am I? I have lost, where am I with my slide? Where am I? Is that along? Yeah. So here am I. Let me finish. Yeah. So here now it's see if I can finish. So here now you're gonna add, so here instead of it just being a positive, it's positive, but its effect is going to be a negative effect. So therefore it's going to be minus 200 from this. So it's going to give you 250. Right? So you're gonna, the difference is 250, right? There. Now you have a positive 250, right? So it's going to come down. So it must come down 250. Down to that point. Let me just clear up that, because we're almost done. So it's gonna give a straight line, and it's a straight line effect it's giving. The only thing you need to remember is coming down straight. So this is 250 to this point. So up here was 450 positive. This is, but remember, it is declining. So that's one thing you need to remember, it's declining. So it declined back down to 250. And remember, these are all what? Newton meter. That's the unit. So you'll have to put the unit in there. All right, from this point now, you have a last part, EB. What is happening at EB? So the next era, this is just simple era. The era is EB, and it's a rectangle again. Let's draw the rectangle again. And the era we're talking about is EB. EB is, what's the era on it? The shear force. It is a minus 250, not true. So it's another minus 250 times 1. So the era must be 250 minus times 1. So it gives me minus 250 Newton meter. So if that is, so here now, for the final part, it is going to be positive 250 plus minus 250. So it must end up back right at 0. And therefore, you just draw it down to 0. See there? Done. And that value probably about 15 marks. Well, that probably value about 10 marks, 10 to 5 marks. This section, this question would value 20 marks in the exam. This is it. This is as simple as that. You can get 20 marks. Just knowing when to draw the curve, and that's all. You don't have to do it by method of section. If you do it by area, get the same marks. All right? Everybody hear me loud and clear? Nobody talking to me. Does it make sense? Do you understand what I did a while ago? So even though this was going up, the positive effect, its effect is really going to be a minus. You must subtract it from the 450. It's going to drop it back 250. Those are the little things you need to remember. With the area underneath your shear force is negative. one thing you need to remember, this is a negative, the negative shear force here, while this is positive. So the value will get up there is a positive value. See there? Positive 700 Newton meter down here. So it gives you a positive moment. The area down here is negative. So its effect is always going to be subtracting from whatever is up here. So this was positive. This is minus, so it's going to drop it 250. This is minus again. This was 250. This one now, the only trick to this one is where this bending moment here. Its effect is going to be a difference between the 550 and this, drop it down to 250. At this point, the same 250 is gonna be here. So add 250 minus and the 250 plus, it bring it back down to 0. Right? Any question? So this point is B. Any question? Did I lose you? Hello? Anybody there with me still?
Yes, sir. Still here.
Yeah, any question? Look too simple? Will you get 20 marks?
No, sir, not too simple, but we don't have any questions. It's pretty straightforward.
Yeah. If you see something like this in the exam, this is 20 marks.
Yeah, man,
Simple.
sir, I get it. Just need some more practice.
Practice it. Me show you all of them. Practice them. And guess what? In the PowerPoint slide, if you go back to the PowerPoint slide that I would have been posting, see I have a question. See it here. This is this question. It says draw the shear force and bending moment. That is it. So this alone is 20 marks. So that is one of the easiest questions on paper. Look on all this one. This one don't have any moment on it. Right? And it's even easier. So all you do, you convert it to a point load immediately. All right. So let's bring this one up. Convert it to a point load, right? And immediately you get that AY is 9.5 and this is 10.5. Because remember, you have 10 up here and 10 up here, so they must add back to 20. Straight. Now, your first thing, this is 9.5, so it come up 9.5 positive. It run the entire span of what? The distance over here. I think the distance would have been the distance would be something like 7.5. What was this distance? This distance is 5. So it's run the entire 5. 2.5, 2.5. So see there? 2.5, 2.5. That I don't know why it's looking like it's not 2.5. Let's go again. Is there CTR says 5.5, so it must be 2.5 and 2.5. The
Yes, sir.
diagram have something different here. I don't know why it have here. So look like 5. All right. It goes over. Let me see.
Yeah, you go over the end of the UDL.
Right, it goes over the L. Yeah, okay, yeah, because this is 9.5. Yeah, just checking it. But so it comes down and it crosses here. But all of this, so it crosses, so you draw it up to here. Good. And it crosses here, come down. So it crosses down at this point. It come down a little bit. It come down. So I think this distance is minus 0.5 because see there, it's 10. It's supposed to come down, Remember, say it's 10. It's 10 supposed to come down. So the difference between 10, so the difference here is what is happening. Is 10, you have 10 minus 9.5. So the difference, it must come down 0.5 down there. So remember, say it's slope down. So it's slope and it cuts it right at, what them call it, 4 point something, it cut it. Some distance there, it cut it down there. So you'll have if you extend it down, it will have been a line crossing the 0. And then it starts, right? So see it here, right? So it cut it somewhere down here, right? So it cuts it, so it goes beyond the distance here. And that is the only little trick to it. You have to remember. So you watch this and you watch the UDL up there. The UDL is 10, so the difference between it wherever, and it shows you that there's a 10 coming down, and this is 9.5. So it must go 0.5 below. So it cut it and drop below the 0 point at minus 0.5. At minus 0.5, right here, so it's gonna run along to where it reaches the next 10. Once it reaches the next 10 here, so this is minus, so it is, so you have minus 0.5 plus 10, negative 10. So it's going to be a minus 10.5. So see there, it dropped down back. See there, and you notice between 5 here, so, and here, see there, so. See, they say you know if you run the UDL all along there, so So if you were to draw the bending moment for this, is the ear underneath that first part first, right? So that would have been, the ear at the triangle would have been what? Simple. You just find the ear at the triangle, 9.5, right? Right angle triangle. And then this distance, whatever this distance is, they work out this distance to what? 4.75, right? Right, because we had cut it, there's a 0.5 difference. And you'll find the ear underneath that. So this would give you a bending moment. That would give you what? So this would be half 9.5 times 4.75. So that'll give you the 22.6. You can check that. So this is 4.75 times 9.5 times a half. So you give you 22.6. So, right. So you give you 22.6 right here. So. And then now, how do you find this little piece that it dropped down? There's a little triangle there. So it is a little triangle come down, which is a little triangle, a little distant there, which is going to be what? This is what? I'll say, it comes down, so there's 4.5 from this is like 0.25, that distant, and then this is 5 minus 0.5. So there's another triangle. You find the area for that, and it gives you, so that area would be 0.5 minus 0.5 times 2.5, it seems like, times a half. So you get 0.06. So you see this 0.06, right? Because half base times height, so it's 0.25 times 0.6, and that is minus, this one, time 0.5, sorry. This is 0.5. Come on, writer. It's 0.5, so that's minus. So this gives you a 0.06, and it's minus errors. So minus error, minus 0.06 from this, right? So it give you back 22.5. So you see, drop it. So you see, it give you a curve. It curve it to this point here. So give back that point. And then now it give you, then the next portion from that portion down to 8, it give you a nice little rectangle, right? So whatever that distance would have been now, what distance are we getting it there now? It's trying to figure out that distance. This distance look like 3. I can check that 3, and then the height of it would have been the minus 0.5. Yeah, check that. So it's 0.5 times 3. How much? So you get minus what? Minus 1.5. There's minus 1.5. Minus 1.5 add to 22.5. So minus 1.5 add to 22.5 give you minus, so you get 21. So you drop it down, and it's a slope. It's a slope. Remember, it's not a curve, it's a slope, because this is a simple support beam over here. So over this side of the beam is simply supported. Remember, simple supported. So it just comes down, you just slope it back down to 21. And that's a part, right? Then on the last piece, this is 21 positive. You're going to calculate the area underneath this. And the area underneath this is going to be, this is what? 2 times 10.5. So that gives you negative 21. So negative 21 between 8 and 10 cancel out this. So when you add the next 20 to it, 21 right here, so you're going to carry right down back to 0. And you just drop the slope right down there. So see, they're done. 20 marks. So if you ask what is the maximum bending moment, you'll be able to say this is the value. What is the maximum shear force? Maximum shear force is 9.5. I could ask you those values. And I could say to you what is the maximum BM. So this is maximum BM. This is the maximum shear force. Shear force max. It's easy as that. How do I know this? I'm able to do it because I'm using, did I bring them over? I'm using these principles. When is a shear force, when is a bending moment, right? Where's my writer? When is a bending moment and there's a simple UDL, see there? Simple support beam, right? See, with simple point load. When you have a simple point load concentration, there's nothing. So the bending moment is just a slope. Either way. And this shear force is just a mapping out a rectangle. See there? Mapping out rectangles. So you have a positive rectangle, you have a negative rectangle. You have this one going up, you have this one coming down. Because once it's a negative shear, it's going to give you that the bending moment declining. But remember, once it's simply support, it's just slope. When it is a UDL now, over here, when it is uniform distributed, the shear force is just going to slope down. See there? And it's going to cross it because the load going to be in the center. It's going to cross that 0 at that point. See there? Straight. So it's half its thing is going to cross that 0 at this point, right? And then it goes up back to here. So if it comes up, see there, it start here at 0 and end back here at 0. Both points at 0. And then now you draw the equivalent. Once it is a slope, it is a parabolic. It's a slope under your UDL, parabolic. Two things you need to remember and it done. See there? Parabolic. You want me getting these over here, but you can look at them. Cantilever, so what it maps out a rectangle. If it's a UDL, see there? Slope, parabolic. UDL, slope for the bending moment, and this one. So all you need to do is remember this page here. Once you remember what happened right here, so then the rest of it is semantics. All right? And see, so you have those to look at. See the example. This one I just work it out. So I'll try and work out the solution and put it underneath it. I don't have it worked out. I have a workout, but not written out properly. I could scan what I have and put it for this solution. That's the fastest way. Otherwise, I'm have to sit down and type it out like this. And then this one here, look at this one. This is another example 5. See the same thing happening here? You get the reactions at A and B, right? And they call it normal reaction. Don't worry, it's the same reaction. You draw your bending moment, come down here. This one copy. So this part is simple first. Come in here, come down, because this is here is 15. So the difference between 15 and 10 is -5. It come down right here, so that comes rectangle, shear force that. So just give you a rectangle. Shear force for a simple support beam, give you a rectangle. For UDL is a slope. So at this point here, it just a slope down. See there, so? Remember, so the bending moment don't come involve yet, you know. It don't involve a bending moment. When you come here, so now, simple support up to 4, it just go slope. Right? Slope. And this the UDL come, see they, wait, look, when it is 15 right here, this is going in the clockwise direction. I will consider, so the effect of it is going to be adding. So you're going to add the 15 to you're going to add the 20 to the 15. So you carry it back up to 35. Remember that? So this one is going this way. I'll show you one going the opposite way, where you're minus. This one is, you're going to add this one. So it add it and it carry it up. So when the moment is going in the clockwise, you add. When it is going the anti-clockwise, you subtract. That's the only thing you need to remember here. And that is the effect that it have on the beam. The simplest way I can tell you to remember it. So here, you go right up here, and then it curves. And the rest of it now is just so between here and here is still a simple support beam, so it's a slope. See there? When it reach right here now, whatever you want to leave and call it, is a parabolic, because that's where the UDL is, and it comes here. So remember, because the area underneath this point would have been a what? A 5. Because 1 time minus 5, so minus 5 from 30, carry back to 35, carry to 30. So minus 5 from 35, positive, gonna give you 30. So it slope back down to that. This is a trapezium. Area underneath trapezium, what would that area be? This look like this is 30 also, because this is 2. This is 2. And the area in trapezium, so this will be minus 5, minus 25. So these two gonna add and give me 30 times minus 30, that is times 2. 2 is the height, times a half. Then you sum the two parallel side, a plus minus 5 and minus 25 to give 30. So you're gonna get back your answer as minus 30. So minus 30 and positive 30 give you 0. So it must come back down here. So see there? Done. So I could do this by inspection. Don't need to do any method of section to actually do it if I understand method of section. If we say use method of section is a total different thing now, where you'll have to demonstrate your use of method of section and you know to come up with the equation. But still, if I'm in an exam and a man tell me to do it by method of section and I don't know method of section, but I still know area, I'm still going to use area to assist me. Right? We can still write down something, but check my equation and make sure me check it by method of area. So method of area is the fastest way to draw your shear force. Right? So for many years now, I've been teaching this course and I've taught both ways, method of section and method of area. Method of area is easier, but you need to just remember certain principle. All right? So I'm saying to the class, I've taught you both method of section and method of area. You can choose in which one you want to use, but if I say method of section, you'd have to have those equations so that when you put those equations between what different points, the range, it falls in place. But it don't mean that you won't get any marks, right? If you do it by ear. Anyway, gentlemen, I am going to run on and leave you. And thank you very much for coming to the tutorial. I will post the video so that all can see what I'm saying. All right?
All right, sir.
All right, man. Bless you. All right. Good, good. All right. So I see you on Friday. We have inertia. We're gonna work some more problem relevant. See if we can tie up the course and then closer to exam. When is it that you have exam again? Remind me. Remind me exam date again.
Sir, I don't remember the date. I will have to look back.
Oh, you don't remember the date. Oh, it sounds like it's way down. Or it's early. I do. All right. You can remind me of the exam date. I don't remember myself. But what I'm saying, I can meet with you guys before for that period. To do a refresher. All right. So have a good one. You hear? Have a blessed one. I'll post the video. All right. So I'm out.